Welcome back to this Friends of Tracking video on how to fit an expected goals model. We're in stage 2 now. Last time we looked at the data involved in modeling expected goals, and we also looked at a simple model based on shot angle and also on distance and how they affected the probability of scoring. So if you haven't already done this, it's probably best that you start with that video that we did last time. But what are we going to do today? Well, I've thought a lot about exactly which level I want to present this type of which level I want to present the fitting of the model on. So I decided the best way to start this was to start by looking at how you fit a straight line. So if you've got some data which you think there's a straight line relationship in, some sort of correlation in the data, how do you fit a straight line to that data? Now that's going to turn out not to be useful in expected goals specifically, but it's going to set up the sort of principles that we use. Then I'm going to introduce something called the logistic function. The logistic function is not a straight line, it's a curved line that goes like this, but it has a nice property that it's always between 0 and 1. So it goes up like that. And that's going to be very useful for fitting to our data. I'm going to then go back to shot angle and distance from goal, which we looked at last time in terms of data. And I'm going to show how we can model that using a logistic function. Then I'm going to show you how to fit shot angle and distance together. And that's going to be the basis for our expected goals model. And finally, I'm going to talk a little bit about how you work with these types of logistic regression models, how you decide if you're going to add different terms to predicting if something is going to be a goal or not. So that's the step for today: fitting a straight line, logistic function, fitting shot angle and distance separately, then fitting them together, and working with regression models, how you put all of this stuff together into practice. Okay, so let's just recap before we get into the details here. Let's just recap on what we learned last time. We made the following figure. We looked at the proportion of shots resulting in a goal. And I said this figure actually, it's important to emphasize that this figure is an expected goals model. It gives the probability or the proportion of goals scored from different places. Now it has some limitations, partly because there's not really that much data. There's one season of football, but it's not a totally comprehensive data set. And one limitation is that it has these sorts of points here where lots of goals were scored, or just there was a sort of lucky occurrence of a goal. There's not many shots taken from here, and when they were scored. And so we wouldn't want to say that if you always shoot from here, you're likely to score, or you'll have a 50% chance of scoring, or so on. So it's got some sort of limitation, so it needs to be smoothed out. But the smoothing out isn't to make it look good. I think I want to emphasize that. The reason for the smoothing out is that we want to base our expected goals model on some kind of underlying understanding of football. And what we found out last time, when we looked at it from a common sense point of view or a football knowledge point of view, is we found that goal angle predicts the probability of scoring. So the more you can see of the face of the goal, the higher the probability you score. And then we looked at that in the data, and we found out that that was a reasonably good approximation. We also found out another way of approximating, and this was distance. So if you looked at the distance from the goal, the probability of scoring a chance decreased with the distance from the goal. So that's going to be our goal today, is how do we actually rigorously fit a mathematical model or a statistical model which predicts things. On all of these plots, we have sort of points dotted around, and we want to put all of those points together to fit some sort of mathematical curve which makes a prediction. And that's really what today's lecture is going to be about, is how do we fit a curve to this data? And the reason I'm going to go into so much detail probably feels a sort of little bit exaggerated detail that I'm going to work through this problem today. The reason I'm going into so much detail is that this is a basic question underlying all of machine learning. So if you can master this question of combining your own knowledge with data into a mathematical curve which fits the data, then basically you can answer most of the machine learning problems that come up in football. So what I wanted to do in order to illustrate this point is start with a very simple example of linear regression. Now, linear regression is fitting a straight line to data. So if you haven't already done so, download the code that's available on the GitHub where I go through a very simple example of linear regression. And I'm going to go through that code now and basically through the steps you would use if you wanted to fit a straight line to data. The code is for linear regression. Start off by just loading in a couple of libraries here. I'm doing the normal thing of copy and pasting across here in Spider. And I've just made up a data set, completely made up just for illustrative purposes. And the idea is we have minutes played in a match and goals scored by various players. And we want to find a relationship between minutes played and goals scored. First thing I do is I set this up into a data frame. So if you go in and you can either see it in Variable Explorer or you can just type minutes model here and you will see the number of goals they've scored. And roughly speaking, the longer they've been on the pitch, the more goals they've scored. So what I'm going to do is I'm going to start just by plotting this data. And that's done in the following way. And now you can see quite clearly goals scored. Lift up this a little bit. Well, goals scored increases with the number of minutes played. And our question is, well, how does it increase? What is the rate of scoring for an average player in this data set? I'm going to actually answer this question by just starting by guessing, actually. Before I get into how you fit it, I'm just going to say, well, imagine you looked at this data and you thought, well, what's a reasonable model here? And it might be reasonable to think that these players score 1 goal per match. If you look here, it's about sort of 700 minutes, 7 goals scored, 200 and something minutes, 3 goals scored. Maybe we can just say that they score a goal every 90 minutes, in which case the slope of this line will be 1/90 and the intercept will be 0. If you've had 0 minutes on the pitch, there's not much chance of you scoring any goals. So the intercept is reasonable to assume is 0. We can put in those parameter values. B, the slope is 1/90 and A is 0. Remember, we're trying to predict goals scored as a function of minutes played. So it's 1/90 rather than 90 times that we have for the slope of our line. So now I'm just going to redo this, but plot the curve on top of the data. And I do that by this. And you can see that my curve, actually, my 1/90 curve, the players score once every 90 minutes, gives actually a reasonable fit to the data. We actually have a straight line that goes more or less through the data points. And we could actually be happy enough with that fit. It feels like, well, a goal every 90 minutes. It seems sort of reasonable for a very high level striker. But what we'd really like to do is actually accurately measure where this curve lies. Where is the true curve in this particular model? I'll do this actually. I'll show these. I can show the distances to the line as well. So let me just run this one more time. If I run it like this, I actually have the points and I have the distances of the line. So the red shows the distances of the line. So what I want to minimize is the distances of the red lines. I want to move this black line around so that the total distance of all of these red lines is minimized. And that's called the sum of squares in logistic regression, because it's a sum of, well, it's the sum of the square root of the distances to each of these things. And that's what I want to minimize. How do I do that? Well, what I use is a library here, the stats models library, which I've imported at the start, and I've called it SMF. And there is lots and lots of different statistical tools in the stats library model. But the one I'm going to use is one that does ordinary least squares regression. And it takes in a data frame. The data is the minutes model. This is the data frame I set up at the start. And it fits a model, goals scored, as a function of minutes played. It fits 2 parameters. One parameter is the slope, and the other is the intercept. Let's have a look at this then. So if I'm actually just going to run this entire code from the start and make it a new thing, and I'll see what happens. So this time, instead of setting up my parameter values myself, I should have commented them out there. commented out those parameter values there. I've fit the parameter values using my ordinary least squares method. If you notice here, I think there's a problem with this thing here. I mean, the line goes through here, but the problem here is that the model predicts that for minutes played 0, players are likely to score 0.7 goals or something like that. If we look at A, we can find out. So it's 0.54 goals is the prediction for minutes played 0. So that's obviously wrong. And I think that's really a case of us fitting the wrong model. If we put in a -1 here, we take away the constant A that comes out of the model fit. So I put in -1 there, and that means that we don't fit an intercept. And then I'll also have to take away A from here, and I'll set A equal to 0. And I'll run this code again. And now I get the best fitted model, assuming that the data goes through 0. And you'll see that it's actually shifted a little bit down from what I had when I had 90 minutes. So 1/90 gave a line which was at a little bit further up there. And if we check, we find that B is 0.01, and if 1/B is 97. So it says actually the best model describing this data is that players score on average every 97 minutes. So when we want to fit an expected goals model, we are interested in fitting a probability of scoring. Now, there's various reasons we can't fit that just using a straight line. And one of the most obvious reasons is that a straight line just continues off to infinity. So the expected goals model gives a probability which has a value between 0 and 1, and a straight line can have values going up to infinity and down to -infinity. So just straight from there, we know that we can't fit a straight line model to relate, for example, shooting angle or distance from goal to the probability of scoring. We need a sort of more subtle functional form, a more subtle curve to fit to the data. And so I just start, to give you a feeling for this, I just start this section. This is section 5 here. Yeah, so let me just start by plotting the logistic curve function. We'll import all of the libraries that we need as usual, and we make a plot here. And this shows what a logistic curve looks like. And you see that, I'll just move this down slightly here. You'll see that we have our X value and we have our Y value here. And the curve goes up like this, and it plateaus, it reaches an asymptote at 1, and it would do the same thing as if we continued the X value in the other direction down to 0. So for every X value, we give a unique value of Y, which is between 0 and 1. This makes it very useful for fitting to probabilities, because all probabilities of scoring a goal, for example, are between 0 and 1. It also, and here where it has a property similar to the straight line, it also increases with one of the variables. We can actually make it decrease with one of the variables by just putting into this function here minus here instead, and it will decrease in this same way. So you can have an increasing relationship or you can have a decreasing relationship. So just to recap here, when we do linear regression, we fit a model which looks something like this. We're looking at Y, which is goals scored, and X is minutes played in this case. And we've got a straight line. A is the intercept and B is the slope. In this case, we actually assume that A is 0 because it makes sense from a footballing perspective. If you're not on the pitch, you can't score goals. And we estimate B. And we do that by minimizing the sum of squares of the distances between the points here and the line. So we could try lots of different lines, and we find that this one minimizes the distances. And that's a statistically correct way of fitting this particular curve, the linear regression curve, the linear curve. Now, when we're interested in probabilities, as I said, we don't want to have a function that can go up to infinity, for example, or minus infinity, because all probabilities are between 0 and 1. You can't have a 105% chance of scoring a goal or a minus 0.7% chance of scoring a goal. All percentages are between 0 and 1. And that's the main reason that we use this particular function. But we're interested in the same thing. Here we were interested in estimating parameters A and B. Here we're interested in estimating parameters B0 and B1. And just to give you a starting feeling for this, this is what the curve looks like for different values. When B0 is equal to 3 and B1 is equal to -3, you get this increasing curve. So already you might be thinking, well, the chance of scoring with angle increased in a way that wasn't so different from this when we looked at the data. So you might want to fit this model. And if you've got a variable where something probability decreases with that variable, as this one does, then this curve might be a better fit. But the idea here is we're going to try and find the values of B0 and B1 that best fit the curve that we're interested in. And to do that, when we do logistic regression, we don't use the sum of squares, and there's various reasons we can't use it. But I'm not going to go into the statistical details of what we can't do. What I'm just going to tell you is what we actually do when we're fitting these curves. And what we do is we maximize the product of the distance between outcome and predicted. So here are the dots here are when a goal was scored. So this is for about, I think it's 100 observations from the start of the data. The dots here are each time the goal was scored. There was 4 goals scored from those shots. And the dots here are the times that the goal was missed. And we have 2 curves here. One of the curve, and they're symmetrical around 0.5 here, and it's because one of them is 1 minus the other. This curve here is the probability that a goal is scored with a shot. So this is the expected goal curve, or it's a suggestion of the expected goal curve. This other curve here is 1 minus the probability it's scored. So these curves here, they're logistic curves. So they have this form here. So for this shot angle, we might be predicting that with a 95% chance you don't score a goal. So we take that distance. And then we maximize the product of all of those distances. So we take all of these distances here between the goals that weren't scored and the probability of it not being scored. And we take all of the distances between the goals that were scored and the probability it was scored. And we multiply all of these together. And that gives us the probability of this particular set of data given the model that we've set up here. And so to find out, and what we're going to do, and this curve doesn't maximize the probability, but the idea is then to maximize the product of the distances between outcome and prediction. Equivalently, that's the same as maximizing the sum of the log distance between the points and the line. Okay, so I'll just reinforce this by going back into Python and showing you some code which makes these various plots. And I think really you need to play around with this for yourself in order to get an understanding of exactly what the fitting procedure is in this case. So to give you a better idea, inside Python, I'll just start by plotting the first 200 shots in the data set, and this is the data set for the English League. So I've loaded in my shot model again, and I've just taken the first 200, and I've plotted, was it a goal, yes or no? So a dot up here means yes, and a dot down here means no. So there's a lot of clustering here. When there's a low shot angle, most of these are not scored. When there's a high shot angle, you can start to see the ratio is more like 50-50, or there's actually a sort of favor in front of goals being scored. Now, I made this type of plot here last time, and this type of plot is taken by looking at the original data, which is of this form, yes or no. I'm basically making a histogram for different distances and seeing how many of those attempts were scored. So this isn't the data that we fit the model to. This is more for illustrative purposes. When we fit the model, we use, exactly as I looked at on the last slide, we use the distances to these different dots using the curve. Now, we can try fitting various models to this thing. A naive thing might be to fit a straight line to it. And here I've just by hand, I've tried to draw a straight line through these points. You can see I've got a reasonable fit. The straight line does go through these points. And you might do, and before the techniques of logistic regression were discovered in the 1950s, people just used to draw straight lines through these data in order to make the best fit. Now, the problem, of course, is that it predicts that for a shot angle of 140 degrees, there's a 120% chance of scoring a goal. Now, this might be okay for a commentator to say, well, he had a 200% chance of scoring that. Or when it was a long shot, he had a minus 10% chance of scoring that. But realistically, we can't have a model that predicts more than 100% chance of scoring a goal. It's just not going to work. So we can't use this linear regression model. And so now let's put in our logistic function. And these are the parameter values that I took before, b equals 3 and minus 3. And we'll plot that one. And now you can see that the slope that we looked at, it gives a reasonable fit to the data. It's not too far away. But we don't know, is this really the optimal fit? Is this the best fit that we can do with this particular data set? And so before I do the fitting, I'll just show you again the plot that I made in the presentation there. This is how we do the fitting. These are the distances between the original points and these two lines, the line being the probability of scoring, which is the expected goals, or 1 minus the probability of scoring, which is the expected misses, actually, this one would be called. And we look at the ones that weren't actually scored, the distance between them and this line, and we look at the distances here between the lines. And the process of logistic regression is a process of maximizing these distances so that the probability of scoring is as close as possible to the actual goals that are scored, and the same for the probability of not scoring. So to do the fitting, we use the generalized linear model package inside stats models. We're interested in fitting the goal as a function of the angle and also a constant. The data we put in is all the data that's inside shots models. And the family that we use here is the binomial, because that's because of this 1-0 nature of the data to do the fit. And that's the proper way of doing this logistic regression. And if I run all of this, I will get a table where the most important things to pick out just now are the coefficients. So B0 is 3.7 and B1 is minus 3.45. Once we have this ground principle that we can predict the probability that a shot is scored based on its angle and its distance, we can use logistic regression to fit all sorts of different models to try and understand what is the best way of predicting a goal. And that is essentially what the expected goals model is. And so I'll show you some of these fits, but here is the example we looked at with shot angle. And this is the best fitting curve to shot angle, estimated using the proper maximum likelihood method. And it gives a model that looks like this. So the probability of a goal is the following function of the shot angle theta. So remember, the angle theta was the angle between the two posts here. And so now we have our best fitting model for that. We can also have our best fitting model for distance. So here I take a single parameter model for distance. Distance is d, it's the distance from this point to the goal. And you can see how the solid line here is the fit. It's also this logistic sigmoidal shaped curve, but it starts coming down over here and comes down here. Now you notice in both these cases, there are points which of course don't lie exactly on the line. There's these sort of points here. Many of them is because there's not many shots with those degrees. There's also this point here, probably not very common either, but there's a goal scored from this type of angle. And in particular, noticed here that the distance, when the distance is 0, the model predicts a 60% chance of success, but actually you've had 100% shot success. And so the match here isn't perfect. So I tried one other thing. I tried, well, here we've just got is a linear function of d, but if we also include a d squared term, So that makes this inside here, it's a quadratic function of D. We get a fit that looks like this. And so it moves up and makes a better prediction here. But that's at a cost of it fitting this point out here and making a worse prediction longer out. And this is why you should really, when you're fitting your expected goals model, you should work both from the geometrical point of view of thinking about what the best parameters are, but also looking at these fits as you go along and finding out what predictions they make. And so here the prediction of the model is that shots from 70 meters out are much more likely to be goals than 40 meters out. And we just know from experience that this is nonsense. There's various ways of fixing this problem, which I'm not going to go into. One of them is you just make a lot of artificial data points that you put out here, which say you never score from 70 meters, because in principle you don't. This is probably a very exceptional situation. And that will correct your curve and allow you to go out there. Another thing is just not to try and fit this type of D squared model in the first place. But there's a balance here. Sometimes it's a good idea to fit these types of things. And so I always work together looking at how these probabilities are plotted, looking at the fits of them and seeing how much improvement you get from adding these different parameters. The next thing we can do is, well, we can actually look at the probability of goal as a function of both the distance and the angle. And that's this final plot here. So now we've got a two-dimensional problem because we've got D and we've got theta. D is the distance and we've got theta is angle. And I've plotted here the probability of goal as predicted by the model. And now we have a nicely smoothed curve, which looks reasonable as well. And it's the best fit to the data. Now you've got no chance of, well, the chance of scoring out a long way out here has become very low, and it increases in a realistic fashion. I've set up a general model for fitting goal probability, and what you can do is you can put in the model variables, angle and distance in this case was what I just fitted. It will add all of those variables to the model. It will, so we'll start with that, just set up the model. The model I have here is that I'm interested in goal probability as a function of angle and distance. I can then fit the model here. And I think it's quite interesting just to look a little bit more at what happens in the statistical fit here. Here I have the coefficients. They're the numbers that I put into the logistic function, the sigmoidal growth function. And here I have p-values for those parameters. So it said all of these parameters give a significantly good part of a fit of the model. So they're all important parameters to include in the model. Here we have a confidence interval for the parameters. What are the minimum and maximum values? And you can see that they don't include zero here. This is somewhere, so for the angle, the parameter is somewhere between -1.7 and -0.8, and so on. Then I've made a little function here which calculates the expected goals from these parameters B, basically using the logistic function. And then I like to do this. I've added the expected goals to my shots model here. And then finally, I create the map, and I just create the map by calculating everything one more time and sticking it into the function. So I need to go back from the XY coordinates I've used for the pitch to the angle and distance coordinates. I do that conversion, and I can look at the probability of goal. And you can do lots of playing around with this type of thing. You can start to put in more variables. For example, if I put in the X coordinate, I put in the Y, I think it's C, I said that's distance from the center. And I run this all over again. I think I'll just do that. You can see here that in this particular model, well, once you've got angle and distance, so if you've got angle and distance, you'll notice that adding X position and the C position, they don't give a statistically better fit. And what this tells you is you have actually got enough information just with intercept, angle, and distance in your model. You don't need to add these parameters. I would encourage you to play around trying different additional parameter values and seeing if they give a better fit to the model than just using angle and distance. You can actually build a model just based on X and C, for example. You can see that this does give a good model. You have all of these p-values are less than 0. So this is a reasonable model. But then when you look at what it actually plots out with this X and C model, you can see that there's a sort of strange effect here where the closer you are to the goal, the bigger the chance of scoring. And you get a triangle here. And I don't think that this is realistic, that you have a good probability of scoring from here if you look in the data. So the fit of the model doesn't necessarily reflect the reality of scoring goals. And ultimately, the only way for you to really understand what's going on inside the logistic regression model is to try fitting these things for different parameter values, making these plots of what the fits look like, and just checking if they're reasonable. I really emphasize this idea that you shouldn't just completely trust the computer to come out with this beautiful fit of the model. You should use both your football understanding and the statistical model to come up with the best particular model. And I think with that, it's good to add another word of warning. I'm using 1 season worth of data to do this fit. When I've done expected goals models in the past, I've typically used maybe sort of 10 seasons of data over lots and lots of different leagues, depending on the particular question that I have. And certainly one thing you can do is you can take the 5 seasons that are in the Y-Scout data and you can fit a logistic regression model to all of those seasons, for example. It'll be very interesting to see. I haven't done this myself, but it would be very interesting to see what the best model is of those things. In some previous work, I did exactly this. I took 10 seasons of the data, and that's where I actually came up with this figure that I showed right at the start. So I took 10 seasons, I fitted an expected goals model, and I looked to see what the probability of scoring. So that comes directly from this figure here. I just basically make contour rings on this figure and fitted over 10 seasons. I think it was Opta data I used then. I found that these were the curves that gave the best description of the probability of scoring or the expected goals. So there is a challenge here in what I've presented, because I want to give you some idea of the theory behind statistical modeling. So you don't just sit there throwing lots of data into black boxes inside Python, that you understand that you're actually fitting curves in this case. But on the other hand, the theory behind this stuff is reasonably advanced, and I haven't really gone into the depth of the theory. And I think for you, you have to get a balance between this geometrical understanding of the system and the statistical understanding of the system. And you only get that through experience, by playing around with these tools in different ways, looking at the curves they produce and so on, going backwards and forwards between these different ways of thinking. Yeah, and I think that's pretty much, has been pretty much a mammoth session today, but I think I've got through everything I wanted to say, but there's still lots more, and we're going to look at that a bit in part 3. I'm going to talk about including other variables in your expected goals model, not just the position of the shot, whether it's a header, whether it comes from a counter-attack. The positions of the defending players is something StatsBomb have in their data. So I'm going to say something a bit about that. Then I'm going to also talk about the limitations of expected goals models, what you can expect to get from them and what you shouldn't really expect to get from them. And that will be in the last lecture in my expected goals series. Okay, thanks for today.